look into it. So last class we discussed up to writing the Lewis structures to P4. Cl2 is very simple one. So if I take 2 moles of Cl, so it will have 7 electrons like this. So to complete its octet, one electron pair will be shared this way. So now you can see the octet is complete for chlorine and the octet is completed for the other chlorine as well. So while writing the bond line structure, we'll simply write a single line here. And you can clearly see that there are three lone pairs here. So number of bond pairs are 1, lone pairs are 6. HCl, very easy one again. I'll directly write this down. So we have 2 electron sharing and chlorine completes its octet while hydrogen completes its duplet form this way. So we'll have this as H and Cl bond. The number of bond pairs would be 1, lone pairs are 3. BCl2, same thing. If you have Be here, correct? So B would be at the center, correct? And B would be at the center and it is connected with 2 electrons sharing with 2 chlorines here, right? Chlorines would complete its octet this way, and you can see beryllium will complete, beryllium will have only 4 electrons here, while chlorine would have 8 electrons and this chlorine would have 8 electrons. Now, what is interesting about beryllium is that no matter how much you try, because beryllium had only, sorry, check. No matter how much you try when it comes to beryllium, it has only 2 electrons to share. So it will make only one pair here. So it is an octet incomplete species. So according to Coastal-Lewis structures, well, this can be a molecule forming, but it will be unstable. All right. So while writing the structure, how do we write it down? So we'll have Cl, beryllium, Cl with 3 lone pairs here and 3 lone pairs here. So number of bond pairs are 2, number of lone pairs are 6. The same thing goes with boron also. Boron which have 3 electrons in its valence shell and fluorine which has 7 electrons in its valence shell. As it start making a bonding as per Lewis structures, first we need to write something symmetrical here and then we will share 1 electron with fluorine just so we can complete the octet of fluorine. So you can notice that the fluorine octet is completed here. So this is fluorine's octet, right? While on the other hand, boron has only 6 electrons in it. So this has octet incomplete again. This is octet incomplete species. So if I write this as structure, I would show it this way that there are 3 bonds with fluorides. Each fluoride has 3 lone pairs on it. So number of bond pairs includes 3, and number of lone pairs include 9. Clear guys? Please check it out. If you have done it, map it up and see if there is any problem. All good? Nitya, Mano, any doubt, beta? Kapil?
No, sir.
Okay. Let me introduce to the other a new term known as formal charge. Formal charge basically suggests that there could be either a real or hypothetical charge present on every atom based on how their valence electrons are involved. Okay. So how do we put that? Formal charge is equal to valence electrons minus half of bonded electrons minus number of lone pair electrons. This is how you would identify. So please check. When it comes to H2SO4 here, so we can say formal, I need to first make a simple skeleton for that. So what I'll do, I'll solve it thoroughly. First, let me write down all the valence electrons present in it. Okay. So you know that two hydrogens will have one valence electron each. Sulfur will have six, 4 into 6. So because oxygen will also have six valence electrons. Okay. So you can see this is total 30 plus 2, 32. So we have 32 valence electrons. I told you that R is an ideal number of electrons required for every element to get their octet or duplet completed. So two hydrogens each should get 2. One sulfur it should get 8. And 4 oxygens each should get 8. Okay. So now 8 5 is 40, 40 plus 2, 40 plus 4, 44. So 44 is the ideal number. But how many electrons do we have? 32. So that makes the electron sharing possible. Therefore, number of electrons shared number of electrons shared will be R minus V, which is equal to 44 minus 32. That makes it 12. 12 electrons are shared, everybody. And because we got a number as 12, so we can also figure out how many number of unshared electrons are present. Unshared electrons. So number of unshared electrons are VE minus shared electrons. This will, I'll call it as bond pair electrons. So this will be bond pair electrons. So which makes it 32 minus 12. So total 20 electrons which are lone pair electrons or unshared pair electrons. So using this, we got a clear idea that how many number of electrons are actually shared uh, structure, during the structure formation. So check out first I'll write the sulfur at the center and then 4 oxygens uniformly distributed and then 2 hydrogens at the end. You might say, sir, why hydrogens at the end? Because hydrogens can only make a duplet form. They will always be at the terminal side, at the end side. They cannot be in the middle. And now somehow I need to make 12 bonded electrons to make bonds. So what are the ways I can do it is this one. See, one option I can do is 1, 2, 3, 4, 5, 6. 6 into 2, 12. So that is done. Correct? So that's all we can do. So at each position, I can make 2 electrons to share. So check out 2 electrons here, 2 electrons here, 2 electrons here, and 2 electrons here. This will definitely complete the octet of sulfur. Okay. And now, how many bonded? Sorry, I have to fix another 2 here. So total 12 electrons done. And now you can also notice that the duplet of hydrogen is also complete. So the duplet is completed here. Here also the duplet is done. Now I need to check out with respect to oxygen. We have a total of 20 lone pair electrons, which means 10 lone pairs, correct? So I need to now distribute down 10 lone pairs. So let me uh, do that here. So I can make 1, 2, and 3 pairs here. 1, 2, and 3 pairs here. Any reason for doing that? Yes, because I need to complete the octet of this oxygen. I need to complete the octet of this oxygen. Both the octet is completed. So far how many I used? I used 6 pairs. Next, I can use 7, 8, 9 and 10. So these pairs are also done. Hence, now if I put that in this order, so you can see this oxygen is also completed its octet and this oxygen has also completed its octet. So this is a perfect structure we could make where all the octet and duplet is perfectly done. Now check this out. While I write the structure, so we will have H with a single bond, sulfur, with a single bond oxygen and hydrogen. Here also we have a single bond. Here also we have a single bond like this. Okay. Rest of them are only lone pairs. Rest of them are lone pairs like this. Correct. These are all the lone pairs present. This is the structure which we have. Clear everybody? Now, what is this one? We got the structure, but it looks little different that sulfur actually had originally 6 electrons, correct? Because the valence electrons of sulfur is 6. But it appears to me that it is only sharing 4 electrons. Where did the other 2 electrons go? Now, this is what the situation will, for solving this situation is what formal charges helps us. Now, let's individually figure out what is the formal charge of every element. Okay. Have you noticed that this hydrogen and this hydrogen makes very, very similar bonds here? This hydrogen and this hydrogen make similar bonds. Similarly, you will notice that this oxygen and this oxygen make similar bond. And this oxygen and this oxygen made similar bond. So I'm labeling them. Okay. So now let me first calculate what is the formal charge of hydrogen. Formal charge of hydrogen as per formula, go back and check. It is valence electrons minus half of bonded electrons, total bonded electrons, and minus number of lone pair electrons, So that is equal to hydrogen has only one valence electron minus half into bonded electrons are 2 and there are no lone pairs on it. So therefore formal charge on hydrogen is 0. And now let me see formal charge of oxygen of one kind. Okay, so that means this kind. These two have similar bonds, so I'm taking that. So valence electrons are 6, half of bonded electrons. See, this oxygen makes 2 electrons here and 2 electrons here. So 4 bonded electrons minus number of lone pair electrons, 2 here and 2 here, total 4. So that makes it half minus 6. Again, you are getting 0. So formal charge of this kind of oxygen, both of them have 0 charge. Next, formal charge of oxygen, second kind. Check valence electrons are 6, half into how many bonded electrons here we have only 2. So 2 bonded electrons. So into 2 minus how many lone pair electrons? 2, 4, 6. So we have 6 lone pair electrons. Okay. One second. Sorry. So we have 6 minus 1 minus 6. So that makes it minus 1, which means this oxygen as well as this oxygen actually carries a minus 1 charge. And now notice the sulfur part here. Okay, of sulfur is 6 minus half into number of bonded electrons. How many bonded electrons? 2 here, 2 here, 2 here, and 2 here. Total 8 minus 0 lone pairs here. Okay, so that makes it 6 minus 4, which is plus 2. So the charge on the sulfur is plus 2, guys. Okay, so check it out. H O S O O O and H. This was the bond. And here I'll write it as minus 1, plus 2. Rest were 0. So since they are 0, I don't have to write it anything. Okay. So this is what we call it as the formal charge, everybody. And I hope you understood how to calculate them. Now, what does a formal charge represent here? See, formal charge helps us realize that there are more with the covalent bonds. For example, to reduce this charge, because our whole idea of this molecule is to have least amount of charge. So what we will do, basically, I'll represent this with a new form of bond, that sulfur, if we have plus 1 here and minus 1 here with O and H, and this side it has plus 1 and with another oxygen minus 1 here. So this plus 1 and minus 1 together, I will make as one bond. This plus 1 and minus 1 together, I'll make it as one bond. And what is that bond here? HO sulfur with an arrow bond like this. This is an arrow bond this way. This way. So this arrow bond is what we call it as the coordinate covalent bond. Coordinate covalent bond. Or the other way we write it is dative bond, also called as dative bond. Okay. So you got to realize that this is dative bond. And based on dative bond, what do we have? We will have sharing of electrons only by single species. Now the arrow itself represent as if that only sulfur is sharing its electrons and oxygen is not sharing its electrons, which does make sense. Go back to the structural design here. So consider like sulfur has one electron here, one electron here, two electrons here and two electrons here. So it means here only sulfur is sharing, here also sulfur is sharing. But here oxygen and sulfur both are sharing. Here also oxygen and sulfur both are sharing. So that's why sulfur has two covalent bonds and two coordinate covalent bonds. Clear? So please go through it once quickly. Check out if you have any term. If you did not understand, I can repeat it back. Right, let me continue now. So, given any case, you should be able to figure out how to put the dative bonds as such. Right. Let me take one example and try to figure again. Let's focus together. I would suggest you work out along with me. Okay. To check. What if I gave you a molecule like H3PO4 and I need to find out if at all there are any dative bonds? What is the formal charge on every atom? Okay. So start working, everybody, along with me. First, valence electrons. So you can see 3 cross 2 plus 8 plus 4 cross 8. Sorry, 3 cross 1 plus 5, because there are 5 valence electrons in phosphorus, and 4 into 6. So notice this again, this is 24. 24 plus 3, 29 plus uh, sorry, 27. 27 plus 5, so that makes it 32. And what about the R value? R value is 3 cross 2 plus 8 plus 4 cross 8. Got it? So how much we got here? So we would get this as 8, 32. Uh, Total, this is 8 5 is 40, 40 plus 6, 46. And how many bond pair electrons? How many we can get? R minus V. So 46 minus 32. So that makes it 14. So how many lone pair electrons? That will be V minus bond pair electrons, which is 32 minus 14. Okay. So that makes it 18. This makes it 18. Okay. So suggest that there are 9 pair of electrons or 9 lone pairs and 7 bond pairs. 7 bond pairs. Correct? So structurally, if at all I have to construct, so I would put this as, phosphorus, oxygen, 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 hydrogen, hydrogen, and hydrogen. This is a symmetrical skeleton which I can make. Got it? Sorry, one more oxygen here. This is a symmetrical skeleton which I can make. And now, see, I can maximum push up to 7 bonds only. So what I can do, 1, 2, 3, 4, 5, 6, 7. Only these many bonds are allowed. So directly I'm writing, guys. So lone pair here, sorry, bond pair here, bond pair here, one bond pair here, one bond pair here, one bond pair here, and one bond pair here. All 7 done. Now writing all the lone pairs. So we have total of 9 lone pairs to distribute. 1, 2, 3, 4, 5, 6, 7, 8, 9. So lone pairs also done. Keep working. Please keep working with me. So now if at all I have to find the formal charge on hydrogens here. So this hydrogen is, all 3 hydrogens are one of a kind. So formal charge on hydrogen will be equal to valence electrons of hydrogen is only 1, half into 2 bonded electrons, so which makes it 0. Next, formal charge. This oxygen, these 3 oxygens are one of a kind, and this is a second kind. So let me see. Formal charge of oxygen of one of a kind will be how many? If you can take any one oxygen and do it, correct? Just a second. Sorry, check. So the oxygen of first of a kind, you see we have 6 valence electrons minus half into how many bonded electrons we have? 2 here and 2 here. So total 4 minus bonded electrons, lone pair electrons are also 4. So that makes it 0. And next, formal charge of oxygen of a second kind. Second kind, okay. Second kind would be 6 minus uh, half into bonded electrons are only 2 and valence lone pair electrons are 6, so that makes it minus 1. And similarly, formal charge of phosphorus valence electrons are 5, half into how many bonded electrons we have? 8, and no lone pair electrons, so that makes it plus 1. So have you noticed something? This oxygen has minus 1, this phosphorus has plus 1. That's the formal charge both would handle. So that can be converted into a dative bond. So hence we have P, OH here, OH here, and OH here, and one dative bond here like this. And the same thing, if I write in a covalent bond form, I'll write this as all POH and POH. If I write it in a covalent bond form, I have to express their formal charges also. So plus 1 and minus 1. Done? Correct? So that this oxygen is carrying minus 1, phosphorus is carrying plus 1. So remember, when you write the same bond in covalent form, you have to express the formal charges also. But if you're writing in terms of dative bond, now you do not have to show what is the formal charge they have. All good? Guys, did you get that?
Yes, sir.
Very good. See, let's do the next one, NH4 plus. If you have NH4 plus, how do we handle that? See, Nitrogen supposed to have five valence electrons. I'll write down without this, without the formula and without solving. And hydrogen is supposed to have uh, one electron here, correct? So problem is we have four hydrogens. So what I can do, hydrogen, I mean nitrogen, and these are four hydrogens symmetrically distributed, and I can put each one with one pair of electrons here. Just a second. Sorry, check. So we have another bond here with hydrogen this way. It appears like nitrogen has completed its octet and hydrogen also has completed their duplet. But since there is one electron missing out of its valence electrons, that's what's supposed to be plus. Or what I can do, see another way to write this is, imagine that nitrogen is actually making three simple bonds here while having one lone pair on it. Okay, this way. So here also its octet is complete. You can see octet is complete for nitrogen and duplet is complete for hydrogen. But then suddenly one H plus came. H plus has no electrons on it. And then nitrogen decided that it will donate the electrons. So it will make a dative bond with hydrogen plus. Okay. So this was H plus. This way, and this way. Correct? Now, remember that I told you dative bond, if you write in terms of covalent bond, it should be only a line, okay, not an arrow, with a formal charge showing that wherever the direction of arrow is, from the starting point, it will be plus one, and here it will be minus one. But hydrogen already has a plus one charge. Hydrogen already has a plus one charge on it. So that's the reason why now it will become N, H, 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 and H, with hydrogen having a formal charge of, sorry, nitrogen having formal charge of plus. So this is the structure that you have to write here. So either you write it in this way or you write it in this way. Both of them are correct. And when you're writing in a coordinate bond form, this is the way you will write. Clear, guys? Next, let's understand about O3 here. Okay. In the case of O3, how many electrons are there? How many valence electrons are there? You can see valence electrons are 6 into 3. So total 18. Ideally, how many we should have? 6 into 8 into 3. 8 into 3, 24. So that makes bonded bonded electrons. How many bonded electrons it must show? So it should be 24 minus 18. That makes it 6. And how many lone pair electrons we should have? So it should be 18 minus 6, which is 12. So this is the simple data which we know. Okay, keep working with me, guys. Okay, so you know that you can make one oxygen in the center, other two at the sides here like this. And I need to make total of how many bonded electrons? 3, which means two pairs. So I can take one pair here and one pair here. So total three pairs are done. So bonded electrons are done. And now lone pairs. So I can keep one lone pair here just to ensure that the octet of this central oxygen is completed. So octet of this oxygen is completed. And then 1, 2, and 3 pairs here, 1 and 2 pairs here. This way, the oxygen and at these ends are also completing their octet. So this octet is done, and here also the octet is completed. So this is ideally how we can expect. So as per the data, everything is matching. So how do we write that? As a structure, we'll write it as O, single bond O, double bond O, with this has two lone pairs, it has one lone pair, and this has three lone pairs. Okay. Now have you noticed all three oxygens are of a different nature? So I'll call this as oxygen 1, oxygen 2, oxygen 3. So let's figure out what is the formal charge on each one of them. Oxygen 1, first kind. It has 6 valence electrons, half into bonded electrons are only 2, minus lone pair electrons are 6, which makes it minus 1. Formal charge of oxygen of a second kind, you can see it has 6 valence electrons, half into bonded electrons are 6, minus lone pair electrons are 2. So that makes it plus 1. Okay. And lastly, formal charge of oxygen, third of a kind, you can see it is 6 electrons minus half into bonded electrons are 4 and minus 4 electrons. So that makes it 0. So formal charge in the first case is minus 1, second oxygen is plus 1, third oxygen is 0. So which means if at all I have to express in a dative bond form, I can write it like this. So uh, first let me write down in terms of formal charges, minus 1, plus 1, and oxygen. This is in terms of expressing with formal charges. Now if I write in terms of dative bond, it will be a dative bond towards this oxygen with one lone pair with double bonds. Here there was double bond with oxygen this way, right? So this is the dative bond form. So you can see there is one dative bond between central oxygen towards side oxygen. So O3 structure is clear. So notice what I can say. Coordinate covalent bond is an acid-base relation between the atoms, isn't it? Why we are saying acid-base? See, the definition of Lewis acid means any species which accepts a pair of electron. For example, in this case, this oxygen is simply accepting a pair of electron. So this can be a Lewis acid. While any species which can donate a pair of electrons, like in this case, this oxygen is ready to donate a pair of electrons. So in that case, it will be Lewis base. So one is acting like Lewis acid, the other one is acting like Lewis base. Okay. So here, for instance, BH3 has an octet incomplete because boron seems to have only 6 valence electrons, while nitrogen has octet complete and also has one lone pair on it. So this lone pair can be utilized to share with this boron, where only nitrogen is sharing and boron is not sharing. So it is as if this is acting like a Lewis base and this is acting like a Lewis acid. And on doing so, you will get a dative bond. And dative bond, if you express in terms of covalent bonds, you will have to write the formal charges also. All good? So this is about covalent bonds and how you need to check out the, coordinate covalent bonds and how you need to understand acid and base concept. Okay, any doubt?
Also,
Boys? Right. Now, let's go ahead and understand these two terms. What is valency and what is covalency? The combining capacity of any element is called the valency. For example, if it comes to hydrogen, right? Hydrogen, the combining capacity of hydrogen is 2 electrons. So, valency for hydrogen is 2. Okay, clear? So, combining capacity of carbon, carbon maximum stretch up to how many bonds? 4 bonds, right? So, the number of bonds that carbon can form, that is called the valency. Okay, or you can also put it in this way, that how many number of sorry, this is bonds, right? One bond, hydrogen is one bond. So how many bonds? So four bonds here, hydrogen is one bond here. So valency of hydrogen is one. So you can either check it this way, or you can check out how many unpaired electrons it has. For example, if it comes to oxygen, oxygen has two unpaired electrons, so that makes its valency 2. That means it will always try to participate its 2 electrons. Nitrogen's valency is 3. Okay, generally it will always involve 3 unpaired electrons. Okay, boron's valency is also 3. It will try to involve 3 electrons in it. Okay, fluorine valency is 1. Correct. Chlorine, same way, chlorine valency is also 1. Okay, and so on. This is the combining capacity of an element. What is covalency? Covalency means what is the maximum capacity to which the covalent bonds can be formed. That means how many maximum bonds it can form. For example, if it comes to hydrogen, the covalency always remains 1, because hydrogen cannot expand to have p orbitals also and make some bonds. So in case of hydrogen, it is still 1. But carbon maximum can stretch up to 4. Oxygen can stretch up to 4. Nitrogen can stretch up to 4. Okay, boron can stretch up to 4. Fluorine can stretch up to 4. So what is the learning from here? That all the second period elements can maximum extend their bonds up to 4. Okay, so that is what is covalencies. Clear? But when it comes to the elements down here, like uh, silicon, phosphorus, sulfur, okay, aluminum, chlorine, in such case, these can expand the valency up to 6 also. They all can expand valency up to 6. Why? Why they can expand so much? Because they have empty d orbitals. Empty d orbitals are available, and that makes it, expand their octet and try to even get towards, 6 bonds. For example, I'll feature some examples here. You can see H2SiF6, known as hydrofluorosilicic acid. In this case, the covalency of silicon is 6, because it is making 6 bonds. Similarly, sulfur SF6, again 6 bonds. PCl6 overall minus, here also phosphorus is making 6. Aluminium. Aluminium can make AlOH 6 times 3 minus. Okay, that is also 6 bonds. Chlorine. Chlorine can make a lot of 6 bonds here, like this. ClO6 3 minus. Correct. So it can make this as ClO3, which is also 3 2 double bonds. 3 double bonds makes it 6 bonds. You can see these are all the cases where they can expand the octet up to 6. Okay, so that is called as covalency. Covalency is that maximum number of bonds that they are able to stretch. Got it? Okay, ClO3 minus to be precise. Okay, done. So if I give you some examples, you should be able to find out that what is the covalency of that molecules. So for example, in H2SO4, what is the covalency of sulfur? H3PO4. What is the covalency of phosphorus? Okay. Then we have tellurium, TeCl6. Overall, 2 minus. What is the covalency of tellurium? Okay. Next, AlCl6, 3 minus. Sorry, F6. AlF6, 3 minus. Got it? Or Cl2O7 on chlorine. Each chlorine, how much it is? Okay. KMnO4 for manganese. ClF3, how much it is? SO2Cl2, how much it is? SiF4, how much it is? SF4, got it? SOCl2, POCl3 for all these cases. Okay. So read it this way. Hydrogens are never directly connected to the center. They're always connected via oxygens. So you're dealing with sulfurs like you're dealing with oxygens like this. Sulfur, and there are two OH groups and there are only two oxygens. This is the correct way of writing actually. Okay. But in the usage of writing the acids, we always write it this way. But this is the correct way of writing. So OH is always a single bond and every oxygen makes a double bond. So we have two double bonds plus two single bonds. So that makes it 6. Here also same way. How do we write phosphorus actually? P, OH, thrice and O. So you can see one oxygen making a double bond and three are making single bonds. So total 5. So 5 is the covalency. Tellurium, all halogens makes only one bond. So 6. Here also 6. Here each oxygen will makes double bonds. So total 14 bonds. For each chlorine, 7 bonds. So covalence is 7 in this case. KMnO4. So here this is K plus. So we can actually separate it out. Okay. So we can have this as K plus and Mn, again O3, and one oxygen will carry that minus charge. The one which carries minus charge will have only one bond. The other oxygens will have three bonds. So that makes it again 7. So here I'm making it 3, 6, 4, 4, 4, 5, and so on. So given any molecule, you should be able to figure out what is the covalency of the central atom. Clear? Right. Fixed covalency. Fixed covalency is, right, whenever we say fixed covalency, that means it will always show a fixed maximum covalency value. For example, if you have nitrogen, carbon, oxygen, fluorine, boron, they can only show maximum covalency of 4. So that is a fixed covalency. Got it? So let me put a few more examples again. NH4 plus H2 H2O. In the case of H2 only 2. Okay. And we can have BF3. Okay. Or BOH4 minus, like this. Or in fact beryllium, oxygen also has like this, two berylliums with oxygen and some nitrate here twice. Okay. So it is like two oxygens are donating bonds to, I'll show you the structure as well. Okay. So here nitrogen, oxygen, boron, boron, oxygen. So nitrogen has 4 bonds, oxygen has 2 bonds, boron has 3 bonds, boron has 4 bonds. Here, see oxygen. Oxygen is like making bonds with two berylliums here, this way, and another two bonds with NO2 and NO2. So that makes total of 4 bonds again. So here also we have 4 bonds. Got it? Okay. We use the term variable valency here. See. Acha, by the way, when do we have this fixed valency? This is due to absence of d orbitals. D orbitals. Okay. The orbitals which are orbitals involved in bonding for first and second period elements. That includes only 1s, 2s, 2p. That's it. 1s, 2s, and 2p. Only these orbitals are involved. Clear, guys? Next. Notice what is variable covalency. So if it comes to H2S, okay, H, sulfur, and H here. So here we will have covalency of 2. So because there is only 2 bonds made. While if you have SO2, okay, so this is SO2. In SO2, you can see it is making 4 bonds. While we have SO3, in case of SO3, we have O, S, double bond O, double bond O. Now this time it has 6 bonds, correct? So if you take H2SO4, so again it shows sulfur will show 6 bonds. So have you noticed that same sulfur is showing 2 bonds, 4 bonds, 6 bonds. So there is a variable covalency observed. So especially when you have, availability of d orbitals, availability of d orbitals helps in getting variable valencies or variable covalencies. Okay. So it will keep on involving all the electrons which are present in it, and it can expand it up to d orbitals. Okay. For example, when it is sulfur in a ground state, we say that sulfur outermost orbit has 3s, it has 3p, then it has 3d. We generally do not write 3d because it is always empty. It's always empty. But now notice something. When it is in a ground state, it has 2 electrons here, 1, 2, 3, 4. This is the valence electrons, 3s2 and 3p4. But then when it has to expand number of bonds, so it has to keep on making more and more unpaired electrons. So we call that as first excited state. When it is about first excited state, then one of the electron from 3s will reach out to 3d. Now it has expanded. Similarly, if I talk about second excited state, then one of the electron from p will also reach out to d, 3d. Now this is second excited state. So remember, the ground state sulfur configuration is 3s2, 3p4. The first excited state is 3s1, 3p4, and 3d1. Second excited state is 3s1, 3p3, and 3d2. Okay. The objective of trying to open up all the electrons and keep it more and more unpaired electrons is to invite more bonding. More the unpaired electrons we have, more is the bonding you can get. Hey guys, did you understand what is variable valency? Please check me. Please check with quickly check out what are the uses of formal charges. See, Lewis structures with less formal charge is more preferred than Lewis structures with more formal charge. Second, Lewis structure with negative charge on more electronegative element and positive charge on more electropositive element is always preferred. For example, if you take N2O, we have the central nitrogen has plus charge, side will have minus charge. Now, if you compare that with this structure, because it has two structures possible, I could write the structure in this format or I could write the structure in this format. Both are satisfactory Lewis structures. But the one which has the charges, the formal charges, negative and more electronegative and positive and less electronegative, that is always preferable. So between these two, this one is more preferable Lewis structure. Okay. Now, what are the limitations of Lewis structure? The first limitation includes the incomplete octet form. So there are many compounds where the central atom has less than 8 electrons in the valence shell. For example, BeCl2, a molecule exists, but it has only 4 valence electrons in beryllium. BeH2, again only 4 valence electrons. BeBr2, 4 valence electrons. BF3, 6 valence electrons. AlCl3, 6, AlH3, 6, and BH3, 6. These kind of molecules which has less than 8 electrons in the valence shell, we call them as hypovalent compounds or hypovalent configuration. Okay. Similarly, we have something called expanded octet. Expanded octet relates to the central atom which exceeds more than 8 electrons in their valence shell. So here we see that there are more than 8 electrons in the valence shell. Okay. Let me take some examples. For instance, if you have PCl5, okay. So to accommodate 5 chlorines, right? To accommodate 5 chlorines, phosphorus has to make 5 bonds here, like this. So 5 chlorines here. So at least I should make one single bond. So count the number of electrons across the phosphorus, shell now. So within the vicinity of phosphorus, it appears to be total 10 valence electrons now. So 10 valence electrons means it is overshooting the octet form. Okay. So now P has 10 valence electrons. So similarly, if it comes to H2SO4, as per Lewis dot structure, we learned that it has HO sulfur with a dative bond and with an oxygen here, OH and H. This is what we learned. But in reality, okay, actual structure, if you notice, correct? So this dative bonds which you have noticed here, they are actually converting into a complete double bond form. So there is a sharing from both sulfur and oxygen end here. And now if you count the number of valence electrons here, so count the number of valence electrons here. So we have 2 here, 4 here, 2 here, 4 here. So how many we got? Total 12. So 12 valence electrons. So it is definitely greater than what do we have for uh, octet completion. Clear? So these type of compounds, okay, these species, which which overtake octet electron configuration, right? We call them as hypervalent species. So earlier it was hypovalent. Here these are hypo. I have written it here. Sorry, these are hypervalent species. Check these examples: H2SO4, SO3, PCl5, H3PO4, P4O10, ICl7. All of these are hypervalent. They all have electrons more than 8. Okay, so these are expanded octet forms. Next, the third of a kind is the odd electron species. Odd electron species means they actually have an incomplete octet by only missed by only one electron. Okay, for example, if at all I have NO, N and O will have, a double bond between both of them. So it feels nice to see that the octet of oxygen is complete. But unfortunately, if it comes to nitrogen here, the octet of nitrogen is not complete. Now the valence shell electrons in nitrogen is 7. So it is just missed the margin by one electron. So now you cannot correct it as well. That means if you are expecting that we can do some correction in it, no, because it has only odd electrons, so we can't make an actual bond. Okay. Same goes with NO2 also. You can see N, double bond O here, double bond O here, and one dative bond with oxygen here. So if I put it this way, and lone pair, right? Now see here, we have 8 electrons for oxygen fulfilling and 8 for, sorry, this is single electron, right? 8 for this oxygen fulfilling. But now if you notice for nitrogen, we have only 7 electrons. So notice that we have 2 here, 2 here, 2 here. 6 plus 1, 7. So valence electrons on nitrogen is only 7. So that makes it odd electron species. Same goes with ClO2, BrO3, CCl3, CCl3 dot, CF3 dot, CH3 dot. These are called radicals. Okay. These are all radicals. So these are all odd electron species. Or simply ClO3, ClO2, BrO3. All these are incomplete due to odd electron species. Finish everybody. So three kinds. Okay. So one is uh, hypovalent, hypervalent, and odd electron species. These are main drawbacks of Lewis structures. Let me just give you a next important concept called resonance. Now, resonance is a concept which will be extremely useful going ahead, in both organic, inorganic as well. To check. It is introduced by Heisenberg and developed by Paulings and Ingold. In a compound, if a compound can be expressed in multiple Lewis structures, that means if a compound can be shown with more than one Lewis structure, then we say it poses a phenomena called resonance. Okay, let me tell you how. For example, earlier we have noticed the molecule O3. In O3, we saw that we can have structure like this, and I'm directly copying from the earlier description which we made like this. And I told you that the octet is complete for this oxygen. You can see these are 8 electrons here, and this oxygen which have 8 electrons. Sorry, I need to put 2 more electrons here. So it has finished this 8 electrons. And then at the center also, we can see this oxygen has completed its octet. Another 8 electrons, right? This is O3 form. So now look into this. We have write this as double bond O and a dative bond O with lone pairs here this way. This is what we wrote as the Lewis structure. Now my point is you could have written the bond this way, Or you could have written the other way around also, right? But say kya farak pad raha hai? I mean, how does it make any difference if I write these two? It makes a difference because consider that between these two atoms earlier you are showing, two bonds. So in that case, the formal charge of this oxygen was zero. But now when you make a dative bond here, now the formal charge in this oxygen will become minus one. So if you have the same oxygens, one, two, and three different kind of oxygens, and here there are those same three oxygens here. So their formal charges is varying in both the cases here. Okay. So if I write their Lewis structures here, so we will write it double bond O, right, with a single bond O minus and plus. Okay. This is structure one. This is Lewis structure one. So I will call it as RS1. Okay. RS1. Similarly, let me write another structure like that, but this time minus charge would be here. So minus here, lone pair and lone pair. Here I have a double bond, no lone pair here. So let me call this as RS2. So there is no problem in expressing with the structure RS1 or RS2. These RS1 and RS2 are what we call it as resonating structures. Resonating structures. That means you're able to represent resonating structures. So you are able to represent the same structure, RS1 and in the form of RS1 and RS2. But these are unreal, these are imaginary structures. This is imaginary, this is also imaginary or theoretical understanding that this is how the structure would be. But the actual structure of O3 would be a mix of these two. So it is neither this nor that, but it is a mix of these two. So how does the mix means? Mix as in, see, there is a pi bond character here and there is a pi bond character here. Okay, that means a double bond character at both ends. So we have to show both cases. And once there is a negative charge here and once there is a negative charge here, because you can see here there is zero charge, here it is minus one charge. So together, how much we are getting it? So we get this as minus 1 by 2 structures. So this delta negative can also be defined as minus 1 by 2 structures. Here also we have minus 1 by 2 structures. So this is how the actual structure looks like, and this is how much the charge that will carry. Experimentally, how do we prove it? We check out the bond length here. See, if you notice that there are more bond means bond length will be smaller. So if I say this as bond length as x here and bond length as y here, okay, and similarly here I call bond length as y here and bond length as x here, correct? But what has been noticed here, the bond length here is actually z, okay, actually z. And what has been noticed that bond length, sorry, this one also bond length as I'll write it as bond length as z here, as well as bond length here is also z. That means both sides the bond length is exactly same. So bond length z is observed to be greater than x, but it is less than y, less than y. So that means single bond is longer bond, double bond is shorter bond, and this bond is somewhere in between. And how much is the value of that? See, if I compare bond order means number of bonds. Okay. X means two bonds. There are two bonds here. And Z means only one bond. So how much is Z? I mean, Y is one bond. It is 1.5, somewhere in between. Sorry, this is the bond order. And you know that bond order, bond length will be opposite to each other. So if the bond order is more, that means more the number of bonds, less will be the bond length. So this clearly proves that molecule, if it has a chance of existing in multiple structures, where it can exist in this form or this form, instead of staying it in only one particular form, it will take a hybrid of both of them. That's why it is called as hybrid structure. This is called hybrid structure. So everybody, let me summarize. The resonance is a concept where you are able to express a molecular structure in multiple Lewis forms. And these multiple Lewis forms are actually imaginary. The actual structure is the amalgam or just the combination of all those imaginary structures together. That definitely showcases in terms of their bond length, bond energies, bond order. They all will be mix of all the resonating structures. Okay? So resonating structures, everybody, is the imaginary or theoretical structures that we write, and hybrid structure is the real structure. Got it? Let me show you with one more example. Suppose if at all I have CO3 2 minus as a molecule and I have to write the Lewis structures. CO3 2 minus can be written as a Lewis structure like this: C double bond O, O minus and O minus. This is one way to write. Or another way to write is C O minus, double bond is actually made by this oxygen and O minus is made here. Another C with O minus and O minus, and this side it is making a double bond O. So this I can write it as RS1, this is RS2, and this structure is RS3. But is this the real structure? No, the real structure would be like this. So basically, oxygens still have at least one single bond between these three oxygens. Then this double bond is kind of a moving between all these oxygens here. This is how it is moving. Okay. So this structure is what we call it as the hybrid structure. Hybrid. Now my objective is to also figure out what is the charges on all of them. Now listen up, how you can solve it. You take reference of one oxygen, for example, this one. So this is oxygen has zero charge here. Here it has minus one formal charge. Here it has minus one formal charge. So add the total charge. Total charge, okay. So charge will be equal to total charge on all resonating structures divided by total number of resonating structures. Total number of resonating structures. So this will be the charge on hybrid. Okay. So what is the total charge? 0 plus minus 1 plus minus 1 divided by 3 such structures. So that makes it minus 2 by 3. Hence the charge here is minus 2 by 3, minus 2 by 3, minus 2 by 3. Got it? This will be the charge. Next is bond order. Bond order on hybrid. That is how many bonds are present between the atoms. Same way here also, total bonds between any two atoms, that divided by total number of resonating structures. Total number of resonating structures. That includes how many total number of bonds. You can see any two atoms, these two, let's say I compare these two. Between these two, we have two bonds here, one bond here, and one bond here. That makes total of four bonds. So therefore, we have total of 4 bonds across 3 structures. So that is 1.33. This will be the bond order. So in here, the bond order is 1.33. Okay. So charge is minus 2 by 3 and the bond order is 1.33. Please notice this. Guys, any doubt?
No, sir.
Right. I would want you to try doing the same thing for SO4 2 minus. SO4 2 minus. Put the skeletons, write resonating structures, write the hybrid, identify the charge and the bond order on the final hybrid. Check carbonate for your reference. Please check. I'll give you a minute's time. Try it for sulfate. Okay, let me write that and show you. Sulfur, which have 4 bonds this way, 4 oxygens. Check if you should get total of 6. Okay, let me show the bonds now. 2 double bonds here and minus here. This is one. Or 2 double bonds here, minus here. Or 2 double bonds here, minus here. 2 double bonds here, minus here. And 2 double bonds on the line, and minus here. This way. Okay. And 2 minus charges here and 2 double bonds here. Done. Check. There are 6 total possibilities. Okay. And if I write the hybrid for the same, it will be we'll have this as SO. So if I have to write the hybrid, this is the hybrid. So we will have to have all these double bonds across, moving across all these 2 oxygens this way. If I have to identify the charge, everybody, look into this. Zero charge, zero, 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 -1, -1, -1. Total -3 across 6 structures. So -3 across 6 structures makes it minus 0.5. So each oxygen carries minus 0.5 charge. Each oxygen carries minus 0.5 charge. That's the formal charge. Now, what about number of bonds? So you can see 2, 2, 2, 6, 7, 8, 9. So 9. So bond order, you can take any bond order. So total it is 9 bonds spread across 6 structures. Okay, so that makes it 3 by 2 or 1.5. So bond order on every sulfur oxygen bond is 1.5. So guys, please check it out. This is how you find out the sulfate form. Any doubt? Now, what you guys need to do is this. Okay, complete the assignment of identifying the bond order, the number of canonical structures or resonance. Canonical or resonance means same, right? To find out for all these cases which I have mentioned, right? This looks very, tedious and obvious job, but it's very important for you to get comfortable with these terms. So I would request you try out these questions. Correct? What you will do, write the resonating structures, write the hybrid, find out the charges as well as bond order. Got it? Right. So we'll stop it here.